approach. And it can also actually adapt it to the case of rigid supersymmetry, but the focus will be on supergravity. I will also try to make contact with first with Cartan geometry and Cartan supergeometry because of the indeed of the characteristic feature of this approach. It's easy to really try to keep contact with the geometric aspects of supergravity. And then I want to move to higher dimensional supergravity theories, which typically involve higher forms, already actually in 4 dimensions that we have the presence of higher form language potential. And so I will focus on the backbone structure of those theories, that is they are described within this approach by what are called 3 differential algebras. Then I will be more specific on these 2. And I will show you how these algebraic structures can be actually trivialized also, and I will also explain what it means in terms of ordinary superalgebras that are called hidden superalgebras underlying the theory. So first of all, let's start from basic introduction. So we have we will analyze both physics and mathematical aspects of supergravity theories, in superspace in particular. So regarding the physics side, let's say, in the late 70s and early 80s, we have the development of supersymmetry and the discovery of the fact that if we are dealing with local supersymmetry, we are talking about supergravity. Gravity is automatically included in this scenario. And a particularly useful framework and adapt framework to deal with supergravity theory is indeed that of superspace, because it allows to, at least under what is my perspective and what is actually proven, the fact is that it allows to have a geometric understanding of supergravity, which is similar to the one that we have of gravity on space-time. And in particular, I want to focus on what is called the supergroup manifold approach to supergravity, also called the rheonomic approach in the literature. It is a superspace approach, and it is strongly based on Cartan geometry. It was initially developed by Niemann and Reggia, and they were absolutely aware of the fact that we're starting from this from this connection with Cartan geometry, and try essentially to develop the supergeometric extension of this framework. And then it was further developed and implemented to reproduce several supergravity results, also rigid supersymmetry results actually, and also to go beyond what was the current scenario to try to grasp more about the geometric structure of supergravity theories in different dimensions and the different amount of supersymmetry by what we call the Castellani-Ravera school, mainly based in Turin. And on the mathematical side, in the late 70s, we have the development of supergeometry, actually in a much broader framework with respect to what we intend when dealing with supergravity theory. So first, it has to really generalization of standard differential geometry, and then implemented also at the physical level, but not by several authors and sporadically, so making this contact between physics and mathematics just sporadically, or at least much less than what it would be actually needed to have a better understanding of the geometric framework underlying supergravity, for instance. And so we have tools from algebraic geometry, shift theory, locally ring spaces, and on the other hand, equivalent approaches, which are more similar indeed to the supergroup manifold approach, which are based on supermanifold, as locally isomorphic to supervector spaces, that is what we would call the superspace. And then we also have categorical, more abstract approaches, especially useful to deal with infinite dimensional superspaces. So
can I ask
yeah.
you, Schwarz, is that Albert Schwarz?
I'm not sure about the name of
right.
Yeah.
Do you know the first name of Borolo? Is that
no.
Theodore? Theodore?
I mean, yeah, I'm not sure.
Okay.
Yeah.
Go on.
Yeah, and also regarding these aspects, I know that they exist, but yeah, I'm saying it should be known much in a much more deep way also in the physics community because of for the power of abstraction and of generalization, not me as per me, I still have to learn all this, so I cannot furnish much.
Sure.
Yeah. And so, regarding when talking about what we are interested in now is the Cartan geometry framework. So, starting from Cartan geometry to gravity level, and in particular to describe the classical Age series of gravity. And the supersymmetric extension of this framework would be Cartan supergeometry, which is well adapted to supergravity theory. And in particular, even then, from the very moment in which we think dealing with higher dimensional supergravity, we have a higher propagation potential, of course, a higher Cartan supergeometry framework would be needed. And so I will try to mention both some mathematical and some mathematical aspects of this framework. So just to keep a bit the contact with mathematics and then show the explicit physical application, in particular of our construction. So the starting point under the mathematical perspective to develop the supergroup manifold approach. So the eunomic approach is that of applying supergeometry, that is flat Cartan supergeometry. And one can then think of relaxing the Murray-Cartan equations. That is, one can think of switching on supercurvatures if you are dealing with super geometry. And this means moving from flat Cartan supergeometry, that is from applying supergeometry, to Cartan supergeometry. And so this is translated into the supergroup manifold approach literature as moving from the supergroup manifold to the soft supergroup manifold, in the sense that this softening of the manifold means moving from flat Klein supergeometry to Cartan supergeometry, in which supercurvatures are there. So this is the detachment, let's say, from the curvatures are the detachment from the flat geometry. And so giving rise to what is called a Cartan superbundle. So what I will talk about today is I will start from the group manifold approach to pure gravity and to Cartan geometry, just to give the basis of the soft group manifold, to make some dictionary. And then after discussing the kinematics, I would want to introduce the geometric Lagrangian for gravity in this framework, and what is and how to build an action, a geometric action. Yeah.
Maybe I missed what does soft mean?
Soft, yeah, soft group manifold, because the one can think of giving, first of all, a manifold structure to a group that is to allow for a differential geometry to exist there and to take limit derivatives. And so this is at the level of Klein geometry, so it's flat, and all the one forms, left invariant forms defined on this group manifold will fulfill the Murray-Cartan equations. When the structure is softened, it is just what is a word that was used from the very beginning by Niemann and Engel, also by other authors in this structure. It just means switching on the group. So it is softened in this sense, the group manifold.
Switching on one?
Curvatures or supercurvatures, respectively. So to describe the
when you say that the Klein geometry is flat, does it have torsion? Or
no, it has no torsion. No, in the sense, because I will mention this in a while anyway, in more details. But essentially, torsion and the two form curvatures and torsion will be switched off in a flat geometric framework. And yeah, so yes, but let me, I will discuss this in a while. And so this just at gravity level, group manifold approach level, to then move to the supergroup manifold approach. And so to extend this discussion and also to see, to show how this geometric construction can be actually consistently extended when dealing with superspace by means of what is called the Rionomy principle, and then how to write what are all the geometric Lagrangian actions in superspace. And also there will be different approaches, different schools of thought also actually in writing actions in superspace. And then now we move to applications, so to the presence of higher differential forms, higher dimensional supergravity, and the three differential algebras, which are the algebraic structure describing the vacuum of the series, an extension of the Cartan equation to involve higher differential forms. And then to this trivialization of pre-differential algebras in terms of ordinary superalgebras, whose dual description is given in terms of one-form fields and involve necessarily extra one-form fields with respect to the structure that we have on ordinary superspace when dealing with higher dimensional supergravity. And we will also see, despite the presence of these fields, how the theory results to be well-defined in ordinary superspace and to have the physical degrees of freedom one would expect with this. One would expect to do that. And then I will conclude with some remarks and possible developments in this page. So first of all, when we think about the Cartan formulation of some theory, sometimes in physics we think just of the fact that we are dealing with differential forms. So rather than a component approach, we have differential forms. While Cartan geometry is more than this, and it is a whole bundle of geometric setup, which is particularly useful indeed to deal with gravitational theories and then with supergravity too. And so the idea of Newman and Range was to study gravitational theories, gauge theories on for gravity group manifold, for supergravity supergroup manifold. So as I was saying before, we endowed the group Lie supergroup or group with a differential structure with the structure of a manifold. And this in particular allows us to define the tangent space and the identity of the supergroup, and to introduce the Lie superalgebra associated with it, which is typically easier also to deal with technically computationally. And so in standard Klein geometry, this term group manifold, which is typical indeed of the Rionomy literature, of the supergroup manifold literature, is actually already there. It's just that it is implicit, and we have a principal H-bundle geometry for G assumed from the very beginning. So the structures are just the same, only different ways of calling them essentially. And so we can define Cartan geometry to be this couple of Cartan bundle and Cartan connection. And the Klein geometry can be seen, yes.
Can I ask you say principal H bundle?
Yeah.
So H is the subgroup that
Yeah.
exactly.
Typically, yeah, Lorentz. And okay, as we will see in a while, actually also when we are dealing with a super bundle, which would be the case for supergravity. Also, they're actually in the fiber direction, so the H would be only Lorentz because there is no way of truly factorizing in supergravity or the fermionic direction of superspace, and so they will span the page. Yeah. And so, as I was saying before, Klein geometry can be the rigid or also called flat limit of Cartan geometry. In mathematics is typically defined and called like that. In physics, it would be just the vacuum, what we call the vacuum configuration of the theory. So when I say like the three differential algebra or the Cartan equations describing the vacuum structure of the theory, this is what I mean essentially. And indeed, in this limit, in the rigid flat limit, we have the Cartan privative bunches. And the Cartan connection reduced to the flat Cartan connection, let's say, so to the one appearing in the plane geometry, and it satisfies the Moore Cartan equation. So we can say that flat Cartan geometry is locally isomorphic to plane geometry. On the other hand, in the same, this is in one direction. In the other direction, we can say that Cartan geometry is obtained by softening plane geometry using the terminology of the group manifold approach. That is, switching on curvatures and deforming the group manifold into a soft group manifold. That is, the Moore Cartan forms are deformed into one form enjoying curvature, and so defining in this way a Cartan connection. So let me see how. Let me show you how this is done in the soft group manifold approach. Sometimes it is said that. Well, actually, the point is that Cartan geometric framework is already there by definition once one picks a specific group, and which is in particular programmatic group. We have already discussed Cartan structure, in particular when we switch on the curvatures. And so here we have the group manifold, which is softened in general. And it is endowed with those one form, which are the G values. So in the algebraic structure, those are the associated curvatures. They obey the Bianchi identities, where these CADC are just the structural constants of the Lie algebra, superalgebra. And the Bianchi identities, we have this derivative that is the whole covariant derivative, so the covariant derivative associated with the soft group manifold, and it is taken with respect to this one-fold field. So this is now I will just show you it's technical, but this is just to show how one thing that at this point should be immediate, that is the way in which we derive from those forms defined on the soft group manifold, how we see that they are Cartan, that they are a Cartan connection. So we consider a subgroup of G. And we have this quotient, G over H, which is the corresponding homogeneous manifold. And in particular, when we consider the soft group manifold, this will be our principal bundle with fiber H and the base space M.
So
then we consider
G tilde is G mod H, or
no, G mod H is the homogeneous manifold on which we model then the base essentially.
right, but
G tilde is the principal boundary. So it is the P of Cartan geometry.
so the full it's essentially G.
Yeah, it's G but softened with this tilde. Yes, it is commonly indicated in this way also in the group manifold literature, and it's just the Cartan bundle actually. Yes. And so yes, we introduce a covering of the basic space, the projection, and the transition functions on as usual, identifying the elements in this way, in such a way, and this means that all the sets pi minus 1 u are glued together into G tilde, into the soft group manifold in such a way that
M is the group manifold or the soft group manifold?
No, G tilde is so we have G that is the group manifold, and essentially we can see it as coinciding with a Klein geometry, so flat Cartan geometry. Then we soften it, we switch on the curvatures, and so we have G tilde, which is the soft group manifold, and it also has, once we say that, okay, we have that H is a subgroup of G, and G over H, this quotient is the corresponding homogeneous manifold, then we can think of the softening of G as a principal bundle, as a Cartan bundle with fiber H and base space M. M is the base space of the Cartan bundle.
So as a physicist, what should I think of it? Where is space-time?
I will show you now when. Yeah.
very concrete. What could it be?
It's
Yeah.
M4 and
Yes,
M4
M is space-time. So it's-
will be identified, is typically identified in the end with space-time. One can construct a theory, write like an action for gravity, integrating over sections of the.
but then I guess the base space M is isomorphic to G mod H or something like that.
Yeah, yes, I mean, it's the model of the, yes, exactly, yes,
But,
yes, I mean, the
but-
flat, the flat.
But isn't that a restriction to the space-time that we can then model?
A restriction in which sense? Because R4.
I mean, obviously we can do flat space, but if I come with some very strange curved space-time,
Yeah,
would
but
that
flat
be
space is would be R4,
Right.
on which M4 is modeled, on which space time is modeled, but it's I mean in the flat case it is locally isomorphic to R4, but in general it is not, and it is just
okay, it's just online without knowing the metric and so on.
yeah, but I will show you also how in the end one can identify it, the base space can be identified with space-time. In principle, it may appear that particular choice, but there are conditions under which, we will see how this is done at the dynamical level. Yeah.
Right, so I mean, this is, you're describing it exactly what you're doing. So you're taking it locally, you have a coordinate patch U alpha.
Yeah.
And in that coordinate patch, the fiber looks like U alpha times H.
Yes,
Right.
yes, yeah.
And everything looks simple, but the whole interesting stuff is when you patch them together. That's
Yes,
where you get your crazy manifold.
Yeah.
Every manifold
Because you are not
looks
attached
like-
to a thing, yeah. And so this is just let's say the preliminary to have the geometric structure well defined. And after that, one writes well, essentially all of these aspects are actually to arrive at a Cartan connection. And so one defines, after having defined this structure, and over each covering we have this map projecting essentially from mapping from elements from G tilde, so from the soft group manifold to the Cartan bundle to H. Given if we have left invariant Murray-Cartan forms on G, and those are the ones fulfilling the Murray-Cartan equations. And on the other hand, if we have this map, so the pullback of sigma on pi minus 1 q, that is in G tilde, we vanishing. So we have this object with vanishing curvature, and on the other hand, we have one form tau, which is defined on M. So those will be, as we will see in a while, those are the objects in physics we deal with in physics in the end. And so if we require the restriction of rho of these forms to be defined in this way, essentially, what are we saying? We are saying that the rho is factorized over the pair G tilde H. And so we are splitting it in such a way to have vertical and let's say horizontal direction. And this is just the way in which in this framework, a Cartan connection emerge. Of course, we have to have matching conditions for tau for the construction to be well defined. Yeah.
Just a technical point, I have a laser pointer if you want.
Ah, okay.
In case it's more convenient.
Okay.
But I see that you're.
Yeah, because I'm moving like, okay, yeah.
Yeah.
Ah,
I don't know what.
thank you.
Hope it works.
Okay, but I hope, yeah.
There should be a switch maybe on the side. There's a button on the side.
Ah, okay.
Is it work?
Yes, it's true. Yeah.
Maybe the switch should be.
No, but okay, this is, yeah, this is already, okay. And so, okay, this is the Cartan connection in the end, and in the group manipulator was called a factorized chain vein. So from this, let's say, generalized field, and let's call it like this, on the whole group manifold, we move to the factorized object, but this is actually induced by the very fact that we have this geometric structure from the very beginning. So this structure is already there. And so this is really how we see it. We have a Cartan geometry behind all of these. And those and tau, which are defined on n, are indeed the gravitational gauge potential, and the matching condition that they have to fulfill for this construction to be well defined are just the passive gauge transformation. So those are the local representatives of the Cartan connection, and are the objects that we are dealing with in the end when we build the theory on space-time, correspondingly on superspace when we talk about supergravity. So these are just examples for gravity. We can take the Poincare group and SG. Then we have that H is SO13, so the Lorentz group, what I mentioned. So this is the corresponding homogeneous flat model. It is the R4, it's the quotient space. Then P, so Poincare, can be softened to G tilde, that we call P tilde, then it's softened. And then it is an H bundle, where H is the SO13 over space-time N, which is modeled over Minkowski space, the R4. And this is the way in which, when we have this structure with the Poincare group, then we can build the theory, the dynamics of the theory. We have, under the geometrical point of view, we have a Cartan-Riemann geometry, and we can build the bosonic pure gravity theory this geometric framework, which reproduces back in the general relativity field equation, right? The Lagrange. And in the supersymmetric level, we can consider the super Poincare groups of gradient Poincare. H again will be SO13. Here we are considering for dimension, and for simplicity, from now on, anyway, I would focus on n equal 1 case. So the homogeneous flat model is R44. Then we can soften G, so to gradient Poincare soften. And it will be again an H bundle over a super bundle over superspace, which is modeled on super Minkowski space. And this is indeed the standard geometric arena for an equal one to supergravity in for space-time dimension.
So is this Klein geometry? Can I find Klein geometry in
Yes.
in the super case?
Yeah, this essentially this first line is the Klein supergeometry.
But in superspace there has to be torsion. That's a sort of in the fermionic part, right?
Okay, bosonic torsion.
No, not bosonic torsion. Fermionic torsion, right? The Q with Q is P.
Yeah.
This
No, yes,
is
okay,
a torsion
okay,
piece.
in the sense, but okay, yes, the usually is that I call it super torsion, TA, let's say, is equal to the covariant derivative of the field bane minus side side contribution. And so in vacuum, that object will be 0. So one would have, because super torsion vanishes in the vacuum.
I mean, flat space supersymmetry has torsion. Flat superspace.
Yes, I agree. Yes, I agree. It's just that, okay, we call that object bosonic torsion just because the fact that is that the super torsion in vacuum is like like a curvature that vanishes. But this means that the covariant derivative of the field band, which is actually a superfield because we are in superspace, is equal to psi psi. And so yes, this is true. We have torsion, but the super torsion vanishes. I will show you what I mean with this. Yeah, because on space time we have curvatures, and then on super space we can define super curvatures. So what happens in the vacuum of gravitational theory, you have both the curvature, the Lorentz curvature, and the torsion vanishes. Analogously, in superspace, you will have that the Lorentz supercurvature and the super torsion vanish. And this will actually imply, even that now the torsion also has a direction, the super torsion has direction along the fermionic direction in superspace. It's true that setting this to 0 is telling you, yes, there is torsion by default in superspace. Yes, and this I agree. Yeah. Yes, yes. But I will show you explicitly the equations in a while. Now will be a bit formal, just to get. So besides, okay, this is okay. This we start seeing now. We start seeing those things that is indeed at the algebraic level we can do this vector decomposition in subspaces. And then it means essentially that we can take the one part that we have defined to the Cartan connection, and its curvature. We can split them accordingly to this. And so we have the split, and this is done with respect to the Lorentz indices, with respect to the Lorentz group. We have rho split as rho AB, rho A, same for the curvatures. And so these are on Pitilda, so on the bundle. While at the level of the base space locally, we will have the local representative of the Cartan connection that splits into omega AB and BA, which are finally the Lorentz spin connection and the phi of n, as we and the soldering formula. So as we are used to see them as differential one-fourth fields. And correspondingly, so these are the curvatures, let's say the curvature and the torsion of the Cartan connection. And it's a local representative. We'll have, again, curvatures and torsion, which will be the Riemann curvature to form, and the torsion to form, which are defined usually as we are used to with differential forms. And what I was saying before is just that indeed in superspace, so this is Cartan, the local representatives for a Cartan geometric framework. In the Klein restriction, so going flat essentially, this is equal to 0, and so torsion vanishes. In superspace, we have super torsion, so this plus psi bar gamma psi contribution. Super torsion in the vacuum configuration, so inclined supergeometry vanishes, and we have indeed torsion is given in terms of psi psi, and this reflects the numeric Cartan equation indeed of the theory, which is due out to the superalgebra, and it reflects the fact that the Amplitude commutator of two superalgebras, so QQ goes into translation.
So how does this square with you had a comment where you said that in Cartan geometry we don't have differential forms, it's general. So but here you're back in differential forms, so why?
Before, sorry, yes, I was saying that we have differential form, but commonly sometimes it happens that when talking about Cartan, the Cartan geometric approach to something, to gravity, to supergravity. In physics, it just comes to your mind with the use of differential forms. But this is not enough. I mean, yeah, of course. So it means that in Cartan, dealing with Cartan geometry, you have differential forms naturally. But the Cartan geometric framework is much richer. It is a boundary structure, and you can really grasp more and understand more on the.
That's not captured by the differential.
Yeah.
It can be representing Cartan geometry and Cartan calculus. Cartan calculus is well represented and we all use it, but Cartan geometry has specific features.
Yeah.
Not as what we do.
And so this was regarding the kinematics. Then we can move on to the dynamics. And so concerning the Lagrangian and the action for gravity theory, we have for instance, in the Castellani book, there and in some review also, there are some building rules for what is called a geometric Lagrangian, both for the group manifold and supergroup manifold case. And essentially there you have the use of differential forms. You involve only the usual ordinary differential operator, the wedge product between forms, and a Cartan bundle, super bundle structure to be there. Essentially those are the rules. And then one can consider, for instance, this is the Lagrangian written on the bundle, still on the Cartan bundle, in terms of curvatures and the one form, the Cartan connection. So this is a core form on P tilde, on the soft group manifold corresponding to the soft conformation group. And then to obtain the action, we need to integrate over a four-dimensional submanifold, because we have a four forms in a four-dimensional submanifold of P tilde, because in P tilde we have the space-time translation that they want to see. This for me is easier to see it into the dual picture, but also 6 directions, let's say, due to Lorentz, and so it's 10-dimensional. And so we can consider this smooth embedding map sigma from N4 to P tilde in such a way that we can write the action as the integral of L4 written on P tilde of sections of P tilde. Then we can rewrite these as the pullback of L4 on M4, so on space-time manifold. And this is precisely the usual the expression of the Einstein-Cartan action that we are used to see. We've just written with differential forms. So this is the field and this is the Lorentz curvature. And so the action defined as the integral of L4 on P tilde over a section is exactly equivalent to the Einstein-Cartan action for pure gravity, reproducing the Cartan-Riemannian geometric framework. So it is typically argued, and also say that it is actually required that this integration is independent of the choice of section that we are integrating on. And indeed, this is encoded in the fact that the requirement for L4 to be basic on P tilde, which means that the curvatures have to be horizontal. So with respect to the vertical Lorentz directions. And so this means that this object, the pullback of L4, has to be invariant on the groupings of M, and it just reflects the Lorentz gauge invariance of the pullback of L4, that is the requirement of gauge principle. And this will be the same. We will see in a while how this extended to supergravity and so to superspace in general. Let me just mention, okay, those are the field equation that we derived, nothing which is again standard pure gravity. So we get that the torsion vanishes, and this is from the variation of the action of from the variation of the Lagrangian with respect to the spin connection, and this with respect to the field length. So we get these equations once written explicitly in component, they are just vacuum Einstein equation. Then let me just mention that one can also think of trying to extend this action and say, okay, I would actually want to integrate over the whole bundle. So not only on this section, but over the whole bundle. And this would mean that, okay, now you are integrating on a 10-dimensional manifold, and so you have to integrate a 10-dimensional a 10 form. So and typically it is written it was suggested to be written in this way, with this no 6, that is a 6 form that also includes now dy differential y referring to vertical Lorentz directions. And this was done actually, well, there is the only explicit way that I know to do this and to recover Einstein equation involves the use of so-called delta forms. And it is explicitly for Lorentz, it is done in a recent review on the group manifold approach delta forms, integral forms by Castellani, and other construction also exist in mathematical literature, but which, however, involves a different object, which essentially replacing this object with a different object that is an 8 form, it has a different geometric structure. So, but this is indeed something that one in principle may think of, and it will be particularly relevant, actually, its extension to superspace, which has recently it has been carried out by Castellani, Catenacci, Grassi, Cremonini, that they are trying to integrate over the whole superspace, which is particularly interesting. I will mention it in a while. So now that what we have seen now can be now extended to the supergroup manifold case. And in the literature, even though sometimes it is not said explicitly, but a principal bundle with Lorentz group as structure group is always assumed from the very beginning. And so the construction goes as follows. We have a supergroup manifold. So now G is a supergroup manifold that will be softened to this to G again, so soft supergroup manifold. But in this case, we have both even and odd coordinates, x and y and usual Bosonian coordinate, y just denotes the Lorentz direction, the Lorentz coordinate, and theta are the odd coordinate. Here we are just considering n equal 1 again for simplicity for dimensions. So we consider a principal superbundle, at least you can think of it in this way, in which H is just SO13, so it's just Lorentz, and the superspace M4 is modeled on the homogeneous superminkowski space with coordinates, and it's spanned by the coordinates x and theta. And so, for instance, in the pure supergravity case, we have the soft graded supergravity. So now we have a Cartan supergeometry framework, a Cartan super connection Rho on grade 1 per epsilon, and tau A, so the local representative of the Cartanian super connection are the superfield defined on superspace with the associated supercurvatures. Now, these ABC are the structural constants of a Lie superalgebra. So, in particular, we will focus on superconvergent algebra case. And tau A, so the local representative of the Cartan superconnection, contains the superfield, which is the orthonormal basis at each point of the tangent plane to superspace. And also omega E, that is the spin connection, but as a superfield. Now all of these objects, so tau A are superfield, and the superfield it has got what we call a bosonic field, which is actually a superfield still, because it has got it depends on x and theta. And psi is the fermionic field. It's the same thing as a superfield. So, but this is the base of superspace. And it is important to notice that these curvatures that are now the supercurvatures of tau will be, and what we will show it in any case, they are horizontal with respect to Lorentz, but not with respect to the Grassmannian fiber, meaning that they are not horizontal with respect to the theta direction of superspace. And this also implies, we will see in the geometric approach, that Lorentz, if we consider local supersymmetry transformations, they are not gauge transformations, but they have to be interpreted as diffeomorphisms along the theta, the fermionic direction of superspace, which are therefore described in terms of the Lie derivative along the supersymmetry parameter x. So the important thing at this point is that yes, when dealing with supergeometry, the basis space is with Cartan's supergeometry, at least in the n equal 1 simplest case, we have that the base is the superfield, and only the Lorentz directions are in the fiber, and the curvatures are horizontal with respect to those directions, but not with respect to the theta direction. And now, in general, I can write, yes.
So, I mean, gauge transformations are diffeomorphisms in gravity. So what is the difference between a gauge transformation and a diffeomorphism along the theta direction?
Yeah, for gauge transformations, one could also think of extracting the gauge part of supersymmetry transformation. And for instance, we can write them as variation of this gauge transformation of a field delta mu, let's say. This is just the covariance derivative of mu, so it has just this contribution. While one can see that supersymmetry transformations involve this contribution plus curvature correction terms. And in particular, these further terms are contraction of contractions of the curvatures along the fermionic directions, and so okay, this is the way in which we see that the supersymmetry transformations have this form. And then one can prove that if we now take the diffeomorphism in the theta direction of superspace, and so we take the derivative of mu, we can see that we get precisely this expression. And so what happens is that when the curvatures are horizontal along a direction for which we are taking those transformation, well, we have that if they are horizontal, the contraction will be 0. And so the transformation will reduce to a genuine, let's say, gauge transformation. But if the curvatures are not horizontal, and this is precisely what happens in for supersymmetry, if the supercurvatures are not horizontal along the direction which we are considering, theta direction in this case, and so epsilon per meter, then we have those contributions, those corrections, and they are written as odd diffeo, let's say. And so this is the way in which we can in general we have that superfield which depend on both x and theta can be written in this way. And the same we can do for the curvatures, for the supercurvatures actually. So we can write an expansion along the different directions of superspace, the x, and then we have the x, the theta, the theta. Those are called inner components and are also the super covariance strength of the supersymmetry literature. While those are called outer components in the supergroup manifold literature, and they are those that are at least along one integer. And so now the point is that when we work in superspace and then we want to compare the theory to the space-time from the content to what we have on space-time. And so we have for the superfield, they induce the corresponding space-time quantity written in this way, and there is this restriction. So once we set theta d theta equals 0 for the superfield, we get their restriction, their space-time restriction. So now the point is that in principle, when we write all the components in the theta expansion of the superfield, we have a priori a new x field. And so looking at the theory written in this way, one should be okay, we have some extra degrees of freedom, extra dynamic in superspace with respect to that we expect on space time, and so there's something wrong. And the theory, if this was the case, this means having a theory that fails to be equivalent to supergravity in terms of local space-time supersymmetry. In this geometric framework, what is called the reorderly principle is the solution to this problem, is the way in which we see that indeed we don't have those extra degrees of freedom, because we have some constraint on the supercurvature that allow for the theory to be equivalent to the one defined in space-time. And so let me show you how it works. So we consider this was called in the literature the reonomic expansion mapping that is telling us from a given space-time configuration, we are able to extract the whole superfield, so to build the superfield, the tau A axis. And so the knowledge of this mapping is crucial to interpret the theory based on superspace as a space-time theory. But knowing this mapping essentially amounts to have a complete set of Cauchy data to solve this problem.
I have not a serious question about the renomic. I vaguely remember in constraint dynamics, there's something called renomic conditions or something like. Is there something? Is it time dependent or not time dependent or?
No, it doesn't have to involve time dependence, but
yeah, I said, do you remember the definition of what I'm talking about?
I'm not, but because this was named reonomy, I think by Ravera,
Yes, my question is really what they have in mind.
Yeah, they have in mind a flow law because the reon, I think it's pronounced in ancient Greek means flow,
Okay.
and onomia is law. So flow law. And they had in mind, they just gave this name, they had in mind the passive interpretation of the Lie derivative. So this flow law from a space-time configuration to a superspace configuration. So essentially this extension mapping. So, and so reonomy for this reason. And all theories exhibiting these properties, this property are called reonomic then. And for this series to be well defined, and so for this the reonomic flow to be well defined, some reonomic constraints have to hold that are those ones. And one can prove that indeed knowing a complete set of Cauchy data to know this extension mapping is equivalent to requiring this. What is this? This is the requirement that the outer components of the supercurvatures are expressed as linear tensor combination algebraically as in terms of the inner ones, that is of the physical one, of the space-time ones, meaning, in other words, this is just telling us that we don't have extra degrees of freedom in a superspace with respect to the theory on space-time. And it just turned out that if we write a geometric action, so if we follow some building rules and we write a geometric Lagrangian, then those reonomic constraints results into, first of all, having indeed the curvature, the supercurvatures in the outer component written in terms of the inner ones. And also the constraint on R being are just the field equations of the theory, so the on-shell equations of the theory.
So
And yeah.
can you take it down a bit? So here you're just writing relations between curvatures, but like if you're not talking about supergravity but gravity, so then you have essentially two different curvatures to play with. You have the torsion and you have ordinary curvature, yes. And then you say, well, choosing the torsion to be zero makes the spin prediction be dependent on the field line.
Yes.
So is there something going on that also
no, it's
here?
a tiny bit, maybe I can show you. Because yeah, it's a bit different in this sense. Considering well, okay, right. Considering pure gravity, what you would have at this level is automatically because because you have a Cartan bundle structure, and so if you write, so we have instead of curvatures that are just RAB and RA definitions. So definitions are RAB is defined in omega AB and RA defines the then, if you then those are this is something that concerns the parameterization of the curvatures, and so it means that just that one would think in principle of having R. So the definition of the definition parameterization RAB equal to RAB mu dx. In principle, one may think of having also for pure gravity, so gravity, RAB, no, EB, X nu plus the same thing,
Oh, you mean
dy dy.
Lorentz group.
The point, yeah, the point is that we already know that the curvatures are, and same for the torsion. So this is actually independent from the fact that, yes, true, if the torsion vanishes, so which means, for instance, to show you how the this is zero, and so you can express the spin connection in terms of the field and then its derivative.
Yeah.
But then, what this means that, okay, this will not be there, and for the torsion, suppose that we have a theory with torsion. So this would be RA mu different from zero, the H mu, this mu. And this is indeed the Riemann essentially, the Riemann tensor RA mu and RA mu, those are the torsion components. Now what happens in superspace is let's consider concurrent. So really the concurrent is just that here we have sidebar gamma A psi, and then we also have the gravitino rho, the gravitino field strength, so the covariant derivative of psi. What happens is that now you still have that Lorentz is factorized, so you will have the curvature, the super curvatures are horizontal with respect to the Lorentz direction. But you will have, let me write it just first to get a bit of space in terms of the field and psi, because it's the basis of superspace, but it's totally equivalent. So ABCD, BD. Plus, and then priori you can have like RAB alpha D psi alpha different DD plus RAB alpha beta psi alpha psi beta. Same for the super torsion, and the same for the gravitino superfield strength. These quantities are not in general anyway the purely space-time ones, because these are the super covariant field strengths. And in general, when we project this on mu, we can have extra components from the other directions. And so what happens is that for the free economy to work, and so it is what happens indeed, is that this component either vanish or are given in terms of BCD or all the other inner components, and typically it is because of supersymmetry, it's actually what happens. So in the case of n equal 1, d equal force gravity, we don't have this term, and we have that R A B alpha D is somehow proportional to rho AB, where rho AB are the super covariant field strengths of gamma. Rho AB are the super covariant field strengths of the gravity. And so this is independent of the off-shell definition of the super curvatures. And so then one can, okay, it's true that typically we build the theory in this framework at first order, but then nothing prevents you from deciding to move to second order formalism for your theory, so to express some connection in terms of the remaining field. So yeah. So okay. And this is crucial because once we have this parameterization, we have the consistency conditions for our theory. And this really amounts to the complete set of Cauchy data for our construction. This is the mapping that we have in the end in the supergroup manifold approach. We have that we can therefore have this mapping from an X space configuration to a superspace configuration, which is called the Rionomic mapping. Then at the level of space-time, of X space, with supersymmetry, we just move to a new X space configuration. Well, if we are in superspace and now we perform an odd diffeomorphism, we move to a new superspace configuration, which restricted to space-time, give us precisely the supersymmetric transformation of the starting, let's say, space-time configuration. A crucial point that I want to mention is the fact that if we now look at the closure of the algebra, of the supersymmetry algebra, of the derivative algebra, this is equivalent to the integrability of the Rionomic constraint, because in general what we have is that we have the D2 closure, for instance, in pure gravity, this is automatic. We have the D2 closure in amounts to check that the Bianchi identities are satisfied by the curvature, and so this is by default. But now we require this parameterization to fulfill the Bianchi identity. And this in turn gives us back precisely the Rionomic constraint. And in implementing this technique, it is precisely the way in which we see the explicit form of the Rionomic constraints. And and so the Rionomic constraints also are now they come from Bianchi. There are no more Bianchi identities, let's say, but Bianchi relations. And they also express the integrability equations among the inner components of the supergroup. These constraints must be valid everywhere in superspace, and in particular on the restriction to the space-time hypersurface.
Okay, can I ask?
Yes.
So this procedure of getting a new configuration by lifting it to superspace and doing some theta transformation, can you give some example? Is it like just like a supersymmetry transformation? Typically what would you change in X space?
You mean this one?
Yeah.
This flow? It's just, for instance, in this example, which was in what I discussed before, was just to show how to really move from an X space configuration to a superspace configuration. It's just to switch on a theta direction. So from space-time to be the source essentially of the superfield.
Oh, okay. And then the line, the arrow is supersymmetry. So you're just getting a supersymmetry transformation.
Here, yes, on space, yes, exactly. On space-time supersymmetry is here. And this is, but then one has, okay, we are in superspace, and there we have the supersymmetry amounts to different in the vertical superspace direction, in the harmonic direction. How are essentially the two related by means of Rionomic? This construction is well defined by means of this flow precisely. Well defined in the sense that we don't get extra dynamics in the end.
Can you get something more interesting, like new, I don't know, new solutions to Einstein's equations or something like that, by allowing something more complicated at the superspace level? Or?
At the level of the dynamics, yes, as I'm going to mention here, right, yes, in a sense, it's something that is studied, that has been studied recently, it's under analysis. And yes, in principle, precisely because of, well, now, having this, also one could think of moving from an X theta configuration to another actually also. And so these are at the level of the kinematics. And then thinking of the dynamics and so of the theory, yes, there are things that can be done. I will mention them immediately after this. So yeah. So this is just one thing that I wanted to add regarding this is that given this construction as it is built in this way, we have that preset because of this integrability condition. We can lift to superspace only those a priori only those configurations that fulfill the space-time equation of the theory, because of and so the Bianchi identities close only on shells, and we can lift to superspace only those configurations which are well defined, whose renomic constraints also give the field equation. And so this construction is valid only on shell in the absence of auxiliary fields, in the sense that if you find any, it is done also in the renomic literature, if you have well-defined set of auxiliary fields that you can use, of course, then you can see precisely the way in which the Bianchi identity results in close of shell, and you can write your off-shell theory precisely within this prescription. So, but a priori, without auxiliary fields, of course, it is just a result of it is the reminiscent of the fact that indeed supersymmetry is on shells. Okay, it was presenting this. And so, regarding what we can do now with this framework regarding the dynamics, we may think of writing a Lagrange. So, and we may think of writing it on the whole superbundle, on the Cartan superbundle, so on the soft gradient Poincare manifold. And so we consider a Lagrangian density, which is the 4 form, where 4 is the form, the differential per degree, and the amount of supersymmetry. And so we may write it, this is analogous to what we have done in the pure gravity case. We write this Lagrangian, and we take the integral of this Lagrangian along a section, a global section of soft gradient Poincare, so superspace. And this can be rewritten in this way, the integral over superspace of the pullback of L44. And it can be rewritten finally in this way, where this is given in terms of the local representatives of L44, it's just pullback of L44. And L44 here is identified with space with superspace in the same way in which M4 previously was identified with space-time. So now we are looking at to gradient Poincare often as SO1 3D principal superbundle. We have basicity, Lorentz invariance of the Lagrangian of the superspace Lagrangian. And so again, we have this freedom of choosing freely the manifold of integration. Then how can we construct such an object? Because the point now is that this object is non-trivial in superspace, and indeed is not the typical object we deal with within the renomic approach. This has been studied more recently, as far as I know, by Catenacci, and collaborators. And how can we construct a full superspace Lagrangian? So taking into account, without even thinking at the moment of superspaces embedded in turn again in a supergroup manifold also with load. So just a superspace. How can we construct this? Well, we use a bosonic 4-form Lagrangian. And we wedge it with what are called, this is an object inherited from the string field theory literature, a picture changing operator. Which essentially it involves delta forms, which allows one to perform in the integral to consistently define it and get rid of the extra directions that one can integrate out of the integral somehow. And in particular, the form written in this way by means of these picture changing operators, which involve delta forms, is an integral form, and it's the way in which you build a top form in superspace, because it circumvents the fact that you cannot start by identity, or in this case, build a top form in superspace. And so this is if one is interested in taking all a bunch of series actually well, with this picture changing operator that typically is chosen by hand. You can write it and just to try to see how it is how your theory is tilted essentially within your bosonic theory is tilted in superspace in a sense. So one can do this, or just to focus, and this is what was originally done in the geometric approach, just to focus on this bosonic contribution. And in particular, one can take it to be the renomic bosonic four-form Lagrangian in superspace, which has the usual neighbors and the right three terms. So derive the field equation as usual, just thinking of integrating. So these are, as I was writing before, just the supercurvatures. These are the field equations derived by this Lagrangian. This is the n equal 1, d equal 4 plus supergravity Lagrangian, just written with differential forms. And then we can just, if we take these field equations and we analyze them along the different components, so 3 field, 3 bosonic field, 2 bosonic field, and 1 psi, 1 field, 2 psi, and 3 psi, so we exhaust all possibilities. We get the field equation written on ordinary space, on space-time, plus the real constraints. And so this already on its own is the geometric construction, and one may think of extending it into a larger group to integrate over the whole superspace. The point is that in its original formulation, in the geometric approach, this Lagrangian is considered to be integrated just over a bosonic hypersurface, which is identified with space-time, and is immersed in superspace, which in turn is immersed in the supergroup. And this may seem a bit ad hoc as a construction, but it is, in the end, it is coherent, because if we are considering this submanifold immersed in superspace, then we can think of having a different embedding, so a tilted embedding. And so this would just correspond to a supersymmetry transform Lagrangian in superspace, plus also possibly a Lorentz gauge transformation, because indeed we are dealing with the superman. The point is that if you are able to integrate and you find, let's say, a vector-changing operator, then you will get, starting from a renomic Lagrangian, all possibly related different realization of the same theory. So, for instance, it was shown that taking for the parables for some theories, it was done case by case, just taking the renomic Lagrangian, finding different picture-changing operators, and you did the change in the picture. That is changing the realization of the same theory, from pure spinors to other formulations of the same theory. So the physical content in the end, whatever procedure one decides to follow, is unaltered. And another thing that is still important to mention is that in general, when we write an action, we have that the invariance of the action, it does not coincide with the invariance of the Lagrangian. And so we have that the diffeomorphisms, the other diffeomorphisms of supersymmetry are an option invariance of the action, only if, within this setup, only if the four-form Lagrangian that we are considering is a closed form in superspace. And there are different constructions in which this problem is also analyzed under different perspectives. So it's not strictly required these to be fulfilled, but some requirements, some other requirements they impose on the Lagrangian, such as boundary conditions. So to have you have supersymmetric Lagrangian up to boundary terms, maybe you have a supersymmetric Lagrangian, or you build a supersymmetric Lagrangian, and then you want to write the action and to see that it is environment under the different conditions. So okay, this was regarding the general construction, and then I would want now to just to give you to show you what happens when we have a higher forms, and so to show you at least one example in which we have the implementation of this geometric framework at the vacuum level. Now we will just focus on the vacuum and to see what happens and what we can do with it this construction. So are there questions on the first part, first of all, on the most?
Many questions, many questions. But I think the most pressing ones were answered.
Yeah.
I mean, so far it seems to me that this is pretty much equivalent to the usual formulation of supergravity and superspace. Except that you have extra components floating around involving the Lorentz directions. But if you project down, you get just the usual
Yeah.
superspace formulation, supergravity.
Yes.
Is that correct?
Yes, they are equivalent. The point is that you don't have, you don't deal with constrained superfields. You don't. I mean, the constraints are on the supercurvatures components, on the parameterization of the supercurvatures.
Right, but that's what you do in the usual formulation as well.
In the end, yes, in superspace formulation, you will have constraints.
Yeah, I mean, you can do it in slightly different ways, but
Yeah.
pretty much the levels.
Yeah, they're.
Is there something that you can do in this formulation that is hard to do in the standard formulation? Or is this just,
Well,
I mean, is there something that you really need this formulation?
to have a better understanding of the geometry, I would say, and to be able to integrate, for instance, if you need to integrate the theory on superspace again in a geometric way, without having to compute Lorentzian and also use delta form. So whenever the geometry is explicit, you can you have a better the only thing is that you have a better control of the geometric features of your theory. And also supersymmetry transformations, because you see them as diffeomorphisms in superspace. And so, well, it's just under the geometric perspective, essentially, indeed, you can reproduce the results that already exist. They have been reproduced. Some new results have been developed. And the only thing is that you have a better understanding of the geometry of the theory. And in higher dimensional supergravity, you have a better control on the homology of superspace. Because of when dealing with the gravitino one-form field, it's a differential one-form field, and you have higher forms which have to live in superspace, have to be well defined in superspace. The homological structure will be captured by the field identities obeyed by the gravitinos in a sense. And so whenever you have some homological structure in superspace, it will be manifest. So, and again, it's related to the geometry, to the quantity that you have on the geometry of the theory. And possibly, okay, this is currently under analysis, possibly, given the trivialization of the geometric structure underlying supergravity theories in the geometric approach in superspace, that I'm going to show you, this construction can be useful for getting new results in supergravity theory, maybe trying to go off shell without involving huge amounts of use of freedom, or it's really a construction that is known in some cases in vacuum, but in the out of vacuum theory, it is still to be developed and to see what can be done. But as far as I know, apart from the mathematical literature in which they are indeed studying abstractly those objects that I'm going to mention, the only literature that I know that is dealing with in this way with the homology of superspace and its trivialization in terms of this algebra is only the geometric one. So, but maybe, okay, still, it would be still interesting to see how within this approach, how it can be translated in, because indeed, in the end, it has to be compatible with whatever superspace approach. Yeah. And so to see and to really understand also which is its relation with other approaches in superspace.
Okay, thank you.
So other questions? So I will now move to the case of higher form supergravity and showing you what I was saying a few seconds ago about this homological structure of superspace. So when we are dealing with supergravity theories, with higher dimensional supergravity theories, actually already in 2 dimensions, we have a bosonic field content that includes, beside the metric, and one from gauge potentials, also P indexed antisymmetric tensors. And an example, for instance, in the dimensional supergravity theory, that is the one we are going to consider in some detail. We have a mu neuron, that is a 3-index antisymmetric tensor, and geometrically it can be written as a 3-form gauge potential A3. Is the superfield strength at F4, and is defined in this way. We receive how, and it was studied by Dove in 1981, 82 in particular. And so this is just an example, but what we have in general is that whenever we are dealing with higher forms, we have a vacuum structure of the theory that can be described in terms of 3 differential algebras. Those were called well, first of all, they were introduced by Sullivan, and then they were reintroduced in the physics literature by Ravera as Cartan integrable systems. They were unaware of the previous work by Sullivan. And then they were also called Chevalier-Eisenberg algebras, homological framework, homology framework in supergravity. And actually, 3 differential algebras is not a proper term under the pure mathematical perspective. It is more, their precise name is super symmetry differential graded commutative algebras. And they are an extension of the Murray-Cartan equations to involve P-form gauge potential. And in the mathematical literature, they have been proven to be related to super and infinity algebras. And in particular, they emerge as a kind of truncation of an infinity algebras. So anyway, let's see what are those objects and how we build this algebraic structure. So this is the construction for a minimal C differential algebra. Let me call them.
Sorry, Lucrezia.
Yes.
Just a curiosity. Is that Fiorenza, Domenico Fiorenza from the mathematical department of La Sapienza?
Yes, it's yes.
Okay, yeah, know that guy. Thanks.
And yeah, so let's see, let me call them 3 differential algebras, and you can use this or this is the way in which they are calling now in this literature. So the construction for a minimal differential algebra, meaning that the differential of any P form does not contain formal degrees major than P minimal in this sense. So at the purely bosonic level, if we have a higher forms, we can introduce those algebraic structures. So we start from the algebra, and we consider Murray-Cartan forms written in this way, so fulfilling the Murray-Cartan equations. Then we construct P plus 1 cochains, Chevalier cochains, written in this way in some representation of the group, where this object here is a constant tensor. So these are the cochains. And then if these cochains are closed, so if their derivative is 0, then they are called cocycle. And if a cochain is also active, of course, it is a coboundary, and we are particularly interested in those cocycles that are not coboundaries because they are elements of the Chevalier algebra homology. And then if this is the case, we can then introduce a new P form AT and write this closed equation, which is a way of trivializing, let's say, the cocycle, because we are introducing it by hand and we are from the outside state, and we are foreseeing this equation. And this is what is called the first term of differential algebra. And after having built this equation, so we start from the cochain that is a cocycle and not a coboundary. We add this P form gauge potential and write this first equation. Then we consider the starting Murray-Cartan forms plus this p-form gauge potential. We search again for co-cycles, and if we find a co-cycle, we add then p-form gauge potential to trivialize it, and so on and so forth. We iterate this procedure till no more co-cycles can be found. And so I will show you anyway this formally, then I will show you now the example in 11-dimensional supergravity. And so these at the purely bosonic level can be extended in superspace, and it is particularly useful, this, as I was telling before, this geometric approach to find non-trivial co-cycles in superspace, because now that we have an object that is the gravity, and we know its physical and geometrical meaning, and the dual as a field spanning the base of superspace, essentially. And so now we have field identities which are obeyed by wedge product between gravity and one forms. And this makes, once we have the field identities, we can extract from them the expression of the non-trivial co-cycle in superspace that we want. And so having this, the gravity themselves as one form spanning the base of superspace makes much easier finding co-cycles in superspace. So of course we have our best then in superspace is the fact that the free differential algebra, once we add the p-form gauge potential, still we require the free differential algebra to be described in terms of fields on ordinary superspace, so whose potential space is just defined by the superfield in such a way not to have extra directions and they have the same physical content that we have in ordinary superspace. And this is equivalent to the physical request of a principal superboundary structure with superspace as base space and the rest of the field that span the fiber. So it is a kind of horizontality condition for the free differential algebra that corresponds to the gauge invariance of the free differential algebra itself. So this is the example of the free differential algebra underlying 11-dimensional supergravity. For this theory, we have this is the I'm writing the supercurvatures, the superfield strand definition on the left-hand side, and on the right-hand side is 0 because indeed it's the vacuum structure. So it's the pre-differential algebra extension of the Murray-Cartan equation. This is the Lorentz the vanishing of the Lorentz curvature, the supercurvatures, vanishing of the supertorsion, vanishing of the gravitational superfield strand. And these are indeed the co-cycles that I was mentioning before in usually when dealing with 11-dimensional supergravity, A3 is the one describing the three-index antisymmetric tensor. And also for writing the dynamical theory, this is enough in principle. But we also have this object. This is the fully extended free differential algebra known for 11-dimensional supergravity. And it emerges, this is a fixed form gauge potential, and it emerges if we take this structure and we see that the closure, the D2 closure of this expression relies on 4 psi field identity, that is on the 3 psi field identity, because if we take the derivative here, D2 is 0, and the derivative of this object gives us psi bar gamma AB psi bar gamma A psi, which is a Pierce identity in 11 dimension, is equal to 0. So this co-cycle emerges from geometry behind the Pierce identity and the gravitinos. And then once we have introduced A3, actually we have another co-cycle, because if we take the derivative of this object, we can prove that it is closed, and it is not an exact form. And so it means that we can add a fixed form gauge potential right to this equation, and out of the vacuum define its field strengths, superfield strengths of 7.
So how does that make sense? Are A3 globally defined? Or it's globally defined?
It's globally defined, yes.
So how can we make something closed, non-trivial closed, not exact? Is that what you're saying?
No, at this level, yeah, I'm just adding, so this object is this object is closed and
Not exact.
I'm introducing from the outside a free-form gauge potential requiring that its derivative in vacuum, only in vacuum, this heaven will be equivalent to this expression. So I'm really forcing this equation is forced in such a way, and in a sense, okay, and this is the way in which this object is introduced because of the homological property of the theory in vacuum. But then, and it is then the free-form gauge potential is the one corresponding and which describes the three index and asymmetric tensors.
So what's the catch? I mean, it seems like you're saying that something which is not exact is equal to something which is exact. Well, what's the, is it because it's equations, what?
No, after this, I will say something similar, but again, is something that is not exact, and it's true because it's just closed. But I'm introducing, I'm kind of trivializing it.
Yeah, you're resolving the homology.
Yeah, exactly. I'm resolving. I'm kind of already kind of trivializing the homology, but I'm adding at the price of adding a new object, which is not there. I'm just saying, okay, from the spectrum, the fields that I have at my disposal, this object is not exact. It's just closed.
Okay, so maybe you mean that it's not exact in the minimal model, but now you're extending your space, and then it's exact in that.
Yes, precisely, yes. And what happens is that those extra fields that you had, then would correspond to those higher fields, the higher fields that you had, then correspond to the anti-symmetric tensors that you have in your theory, and they reproduce. But in principle, for instance, they can be added also in theories. For instance, in d=4 and =1 pure supergravity for going off shell. Well, it's there in those models, but introducing a complex free form. Free form of course, it's not precisely because it's not a dynamical in four dimension. It's a way for together with other things, of course, but it's one of the addition that one can do to the theory to go shell. And the way in which it is built is precisely the same. Minimal theory, the amount of fields that I have in the theory are those, and this object is closed. But I introduce something else to trivialize the homology and to make it exact, at least at the vacuum level, and of course out of the vacuum I introduce an object which is the field strength, so there. Okay. And so this six-form gauge potential is related by conjugality to the field strengths of A3 on space-time. And so in the end, once you write the 11-dimensional theory, usually I've never seen, as far as I know, no construction involving B6, but just A3. And it might be that it's a kind of dual construction, like let's say A3 is electrical and B6 magnetic, something electric and magnetic duality, something like that. So in principle, the two constructions should be equivalent. So even though the only one developed that I've seen explicitly developed is this one here, A3. So what I want to discuss now is this construction, which was introduced in 1982 by Ravera and Cartan. And so the question was, can now I have this pre-differential algebra underlying the vacuum structure of the theory. So can this be traded for an ordinary Lie superalgebra, so written in terms in the dual description just of one form field, bosonic and fermionic one form field, and so of a hidden superalgebra? And the answer is yes. And at least locally, this is described by a supergroup manifold, which is called hidden supergroup. And in principle, so once we have this construction, this trivialization, in principle, we have two possibilities. Either we just take our theory with higher forms and they will be written, as I will show you, in terms of one-form fields dual to the ordinary superalgebra description. So I replace their expression and I go on with the theory like that. Or other possibilities to say, okay, I have found something that at the vacuum level is fully equivalent to my description involving P-form gauge potentials. And so now I forget about them and I construct and I go and I reconstruct my theory directly from this supergroup manifold structure. So taking this as a starting point for the construction of a supergravity theory, and so the vacuum structure, the associated field strengths, and so on. In particular, this construction we have also analyzed it more recently, and the point is that this trivialization that we show you involves the presence of extra spin or one-form fields. So not only extra bosonic one-form fields, but also extra spinor fields carrying spin major than 1/2, typically, so spin 3/2 from what we have seen now by model, let's say, analysis. And so we have further analyzed, so the bosonic field appearing were interpreted in terms of M2 and M5 brain sources already in antecedent literature. But the role of these extra spinors was not clear, and so we did a step further in this direction, showing that under a group theoretical perspective, it ensures that the new form fields that we have, the extra fields that we have, do not carry physical degrees of freedom. So they are just fields that are necessary because of supersymmetry and because of the construction for this trivialization to be done, but they don't carry extra degrees of freedom. And also let me tell you also that this trivialization that I will show you is not unique. There is not a unique way of performing it, and it is in the mathematical literature. Differential algebra are really related to an infinity superalgebra, and that's what is referred to as a higher stack. And the hidden supergroup or hidden superalgebra, so the hidden supergroup is referred to an atlas for such stack. And so it is also interesting under that perspective to better analyze what is happening geometrically to really see what it means to have different trivializations, because indeed it's not unique, the trivialization, and what it means physically and geometrically to have different trivializations of the pre-differential algebra underlying supergravity theories. So this is the example of, again, also for this for the trivialization of pre-differential algebra, we show you the 11-dimensional case. We have also explicitly analyzed the 7-dimensional, 4-dimensional case, and it's a procedure that in general can be performed. There is nothing preventing you to do it whenever you have a higher form field. So this is again differential algebra in 11 dimension. It involves fully expanding. It involves this field, and it is invariant under the form gauge transformations given in terms of a two-form gauge parameter and a 5-form gauge parameter. So the double investigation was this one. I will show you the recipe, let's say, for seeing if this pre-differential algebra can be traded for an ordinary superalgebra. So essentially, they associated to A3 and B7, B and B are the symmetric in 2 indices, and B1 and 5 are the symmetric in 5 indices. Those are bosonic one-form fields associated with the presence of A3 and B6. And so, and I will also tell you what are those objects there. They were already known somehow in the algebra literature. So then we take these as the basis of our Cartan forms. So in vacuum, now we have the superfield and spin connection and these two extra fields associated with these extra Cartan equations. These also show us why to choose precisely B and B1 and 5, because the Peirce identity, structure is reminiscent of the irreducible representation of the non-vanishing fermionic bilinears that we can write in superspace. And then the higher formulation potential that we can add in the series I showed you for building a differential algebra is reminiscent of the first identities. And in the same way, the one fields that we can associate with A3 and B6 are reminiscent of, well, essentially the Cartan equations are given in terms of the fermion bilinears that are non-vanishing in superspace and in 11 space-time dimensions. So gamma, A, B, gamma, A5 are gamma matrices in 11 dimensions. Then the third point is to consider now our free-form gauge potential and consider, let's say, an ansatz for it in terms of those one-form fields with all possible combinations that we can write. And so this is the result that we can. This is what we can write with these forms for A3. These are, in principle, three parameters that have to be fixed. How? Requiring that this ansatz, this parameterization of the free form is indeed a good parameterization in the sense that it fulfills the bound differential algebra requirement of ordinary superspace once we take the derivative of the three written in terms of one forms. And so this was the procedure, and one can show that indeed it is not possible to reproduce, there's no way to reproduce at this level the free differential algebra on ordinary superspace, unless we also introduce an extra spinor, a spin 3/2 field. And this is something that we don't have the proof that it's let's say a mathematical clean proof that it always happens this way, but for the models that we have analyzed at the moment, it is always the case of to express A3 in terms of one forms and to fulfill the free differential algebra structure, we have to include a spin one form field such that it fulfills this Cartan equation. So the D2 of this expression forces it's we have essentially one coefficient which will be the normalization of it, and the other two that are fixed by this equation and by the requirement by this requirement. So now we include this extra spinor in the parameterization of the free form. We require again dA3 of sigma to be equal to psi combination that we have seen before for the free differential algebra. And we get that indeed, yes, we find a result. That is that all the coefficients appearing in this expression are actually fixed in terms of a single or one free parameter. And I will also tell you briefly at the end what does this parameterize.
In the previous ansatz, why didn't you have terms with psi in them?
I didn't, because because when you have to take into account both the form degree of the object itself and also the length dimension, the scaling dimension of the object, and assuming that the parameters they don't have to carry scale dimension, then you get that you can also include the psi terms like psi and some other field will not be possible because given also their dimension is one essentially because psi is 1/2, and so on, and you see that you cannot add those terms. While if you include also indeed, you can write term of this time psi RB, well, yes, psi beta terms.
So again, how is this different from a standard formulation where I just take psi to be d theta? And then
Psi to be
d theta.
But these, okay, psi will still be d theta in the sense that psi will still span the basis of superspace. Here you are enlarging superspace with extra directions that are both given by the bosonic one-form fields. So geometrically, you are adding those.
But those would be explicitly constructed now as theta, gamma, d theta.
Which are.
You can explicitly construct those b. If I say that psi is d theta, and I can explicitly construct those b's as bilinears theta, gamma with a bunch of indices d theta.
like this.
And then I.
But you
can do all
mean,
this
you mean something like this?
Yeah, I just solve those equations would be explicitly now.
Yeah, the point is that, at this level, I mean, it's not enough to define the object itself, but you have to check that you don't have extra degrees of freedom in the theory, and so these have to be the case both for BAB, BA1 and
Yeah, but if I express size d theta, I manifestly don't have any extra degrees of freedom.
you have to check how it transforms also under gauge transformations. Well, you have to check that the gauge transformation, the original gauge transformation for the free differential algebra are reproduced within this construction where indeed, yes.
But it's really just flat superspace. It's just flat 11-dimensional superspace. I can explicitly construct the gauge potentials. But yeah, I don't see what the difference is to that. I mean, this is just a more abstract way of writing the same thing. Instead of d theta, I write psi.
So what
You know,
what is the eta
uh,
in the number?
again, it's theta, gamma, and d theta or something like
But you will not, okay, maybe I still, okay, there are similar constructions, so, but would you agree that at this level anyway, you are left with extra directions that you don't have in ordinary superspace? Because despite the fact that the free differential algebra is still defined on ordinary superspace, because I'm asking it, so I'm taking the derivative of A, and I'm explicitly building the thing to be the case. But still, given this definition of the Cartan equation associated with BA, BM1, and eta, I'm adding extra direction to superspace still. The theory is defined in ordinary, well, I mean, the right-hand side, let's say, is the ordinary superspace, but I'm having extra fields.
But you want to think of these V's as adding some extra fields,
Yeah.
but the calculations are isomorphic to the case. Size, theta, you get all the same calculations. I mean, I understand you can do it this way, and formally define new fields, and in the end, find that they're constraints of didn't introduce anything new.
So, okay, if you do these, well, first of all, the point is that asking for gauge invariance of the free differential algebra will fix the way in which the extra field has to transform the form, and also will give eta an explicit role. So these are actually to be checked explicitly. And in a second fact is that actually this form of eta is not fixed a priori, and the result that you get for really having the theory is equivalent to your free differential algebra is that you get a familiar solution actually with one parameter still in the theory. So I mean, it might be because, for instance, at a certain point there was a moment in which we were thinking, okay, now that we have this construction, can we try to switch on non-Abelian charges and to kind of introduce a kind of cosmological constant in 11-dimensional supergravity, starting from this trivialized structure, so from this vacuum structure and switch on, and then build a series of. And so the point was to check if there is some algebraic structure still with 32 supercharges that can allow in some limit, given that we have a free parameter, in some limit to reproduce this structure. And okay, the answer is no, but there are indeed superalgebras built in this way. I mean, just saying d eta is okay, it has to introduce to have an explicit scale appearing in the parameterization, but then deep side. And so somehow all fields like torsion deformation or SP132 are of this type in a sense. You have extra fields, but you have that your algebraic structure is fully fixed. You just have one superalgebra that you build in this way, and indeed you have that the extra fields that appear. They have the Cartan equation that you have are just written in terms of this field and of the object. I mean the vacuum structure of the theory, which in vacuum gives you But here it's a broader construction. I mean, you don't have a unique solution. You don't even need you don't even have in general a unique way of trivializing the free differential algebra. In this case, 11 dimensions is a bit peculiar under this perspective, but you get a family of solutions. And so how could you get these just by saying I have recent, well, I just try to solve the Murray-Cartan equations. If you don't check for both the gauge invariance and reproducing the theory in ordinary superspace. So I don't see, I mean, it can be that it describes, well, maybe this is the way in which you can introduce a vacuum structure for higher dimensional supergravity theories based on some different algebraic, fixed algebraic structure. The way the thing that you were describing, but
Yeah, I just don't see the need of introducing all these extra fields there.
no, but in principle you don't, and also in principle you don't need to introduce them, because the point is, whatever prescription I decide to follow in superspace, I will have to deal with antisymmetric tensors at a certain point with higher dimensional supergravity. I can either introduce them in some space-time description. I can deal with superspace and introduce them. I can deal with the geometric approach and introduce them. And you deal with P forms. And also you build the Lagrangian, you study the theory that way. But the question is, okay, now that I have these higher forms, is there some way of seeing the same theory, which involves higher forms, as a theory just with one form? So it's really a supergroup manifold. And also because in this sense, it's also, in a sense, it's thinking, is there some combination of degrees of freedom carried by one form field that can allow for the same description that I obtain with higher forms? And so a kind of rearrangement of degrees of freedom able to reproduce the same theory, but to trivialize, so, and also in a sense easier to deal with and with more freedom under several perspectives. And the answer is yes, and but not only, even, I mean, it's not unique, so there are some ways in which you can do it. And also in cases, in peculiar cases such as the 11-dimensional one, in which it's more strictly choice, still you have a 3 parameter in the theory. And so,
okay, so you want a theory involving one form, so you want to get rid of the
Yeah.
3 form and replace
yes,
it by one form.
it's a choice. Sure, in the end, you have at least when you build the vacuum structure, which all of these are just checks to say, okay, are we still describing 11-dimensional supergravity? Yes. Okay, so we can go on and see what happens. Yeah. Yes. No, that I absolutely agree. One is okay. I don't care about this trivialization, this construction. I'm just happy with the higher form description. Yes. And okay, so this is the trivialization. So this is the result we get in the end. Is the basic of one form field. This is the dual description in terms of generators. And so this is the exactly, okay, I've written it here. This is well, besides the super concrete part, we have this. And it is the hidden superalgebra underlying 11-dimensional supergravity. This structure, which is just the ordinary superalgebra, is equivalent to the free differential algebra. And it involves this Q prime that is dual to the extra spin or eta. It is the nilpotent, and it appears also in this way. And this part in this box essentially is the algebra. And so, so that AB, the one in 5, were later were then understood as n-brane charges, sources of A3 and B6 respectively. And the role of eta was much less explored. We analyzed it in some detail, and I conclude by discussing it. And also, which is the relation between the algebra and the Ravera algebra, we call it like this. So the point is that the Ravera algebra, which is the hidden superalgebra underlying 11-dimensional supergravity, is a spinor central extension of the M algebra. So it emerged in this way, and of course, then one can start thinking of building the relation between superalgebras involving 32 supercharges to see how they relate.
Q and Q prime anti-Q.
Yes. Yeah. And in general, in some cases, so this is not the case in 11-dimensional because one would need a scale. That was one of the things that we tried also to do, but in other theories, one can introduce also actually non-trivial anti-commutation relations between Q and Q prime.
I'm sorry to interrupt here, but I'm supposed to teach.
Oh. Okay.
So if you can wrap it up, maybe.
Yeah, how much?
No, I will, well, maybe just to show you which is, I will tell you which is the role of this eta, and I think that that was my point. So maybe, yes. So the point is visually, it is this essentially. So once we have the extra field, the base of superspace extended with this extra field, Q prime, so this is the dual version of that the extra spinor field allows to project those extra directions in the files essentially. So to have the same degrees of freedom and to have a differential algebra defined in ordinary superspace. And okay, this is the way in which it happens in some detail. Essentially, once we study the gauge invariance of the free differential algebra, so because we also have to see how this extra field transforms, and if they transform properly in such a way to end up with our structure to be well defined. And so what we get is that indeed, with this construction and with eta transforming in this way, we get indeed the gauge transformation of the three. This is done for the three forms. So the three forms written in terms of one forms is a Lie derivative along this direction of the three forms. And so it's well defined as genuine diffeomorphism along the fiber direction of the manifold in superspace. And even though we don't know the parameterization of B6 because of computational difficulties, the same holds true also at the level of gauge transformations, or it also, we have proven that it also true also for B6, and so it is well defined that one should of course would be nice to have the explicit parameterization of B6 too. And the final point is that, okay, the open question that I left before was what is what does this free parameter that we find in the parameterization parameterize, and we can split A3 into two contributions, same for the extra spinor, and so into two extra spinor, let's say. And one of these contributions is the A30 is responsible for the four-form homology of the supersymmetric free differential algebra, while the other one is trivial. And so these three parameterize precisely the homologically trivial deformation. And one can prove that this is related to OSP 132, and it's the way in which in this geometric analysis we can see that we cannot let's say switch on a cosmological constant in 11 dimensions, so introduce a scale in a pure 11-dimensional supergravity, because when we describe its free differential algebra, in terms of one form, we have this parameter, and this contribution is the one responsible for this is residual somehow from OSP 132, and this contribution is responsible for the range of OSP 132 in the sense that it does not involve the 1 in 5, which is there in OSP 32, and so it's the piece that really breaking in the sense that it doesn't make this structure compatible with the OSP 132 superalgebra. So there are some relations between the different superalgebras involving 32 supercharges. And this was what I was telling you before, the relation between the M algebra and the Ravera algebra. And these are other algebras involving these extra fields, but still having especially having no direct relation between the DF algebra. So the only way in which this can be reproduced is from the M algebra with the eta extension, or if we want directly from the trivialization of the free differential algebra structure. And so, and then we have analyzed the same theory in 7 dimensions. We have found similar results. There we have mutually non-local higher form potentials and Lagrangian subalgebras. And so we have 2 Lagrangian subalgebras, and then we have found 2 extra spinors. So it might be, we expect something similar to happen also in 11 dimensions. We didn't have it explicitly yet. And so, yeah, this is just to conclude that both under, so we have seen how to move from Cartan geometry to Cartan supergeometry. Well, actually, better said from gravity to supergravity within a Cartan supergeometry framework, or that is the supergroup manifold one. And so also the way in which geometry and kinematics can actually be relevant, and a better understanding of the geometry can be relevant in also understanding the interplay between different degrees of freedom, as I was mentioning before, at the level of the free differential algebra and its trivialization. And so, if maybe something can be gained in moving from off-shell descriptions of theory. And we have already, under this perspective, some results, but in simpler theories. That is the equal for equal one, where we know that off-shell is here. And other possible open direction, especially in this context of trivialization of free differential algebras, where to see these extra spinors as the possible tools also to adopt in generalized geometry, and so on, because of the way in which they make this hidden supergroup to actually look at as a super bundle, super fiber bundle. So if these are indeed a dynamical way of implementing the section constraints in generalized geometry, and also if those extra fields can have something. We have analyzed the theories in the presence of unknown one, so here I added the adjective topological. But anyway, if these extra fields have something to do with auxiliary fields and can be interpreted as auxiliary fields in off-shell formulation, supergravity. So, thank you.
Thank you. So I think we leave the questions for later, because we are occupying space for the viewer.
That's okay, I'll take it. Yeah, okay. All right, so, hello, Giacomo, Stan.
Okay.
Yeah. We put out board, and probably ask Giacomo to stop recording.
So
Yeah.
did you say something?
Yeah, can you stop recording? Yeah, that's it.
True.
Well, you record this like